So, hello everybody. We are just in this short review of some standard statistical methods that we have created a data set of 15 data points, and now we want to go into the data and describe this data via calculating general means and also then calculating measures for the shape of our distribution. And then further on, we want to go that we create another data set, and then we will talk about so-called contingency tables, so correlation between two kind of data sets. I don't know, have you done in your introductory courses? Contingency tables? Have you dealt with them? Okay, good. So then this will also be a little review. So we had calculated the arithmetic mean and the geometric mean, and yeah, then I have posed to you this question here. Has anybody of you done this? What is the average velocity if I'm going from Oldenburg to Wilhelmshaven with 100 kilometer per hour and then back the same distance with 50? So then let's do it together. How to calculate the average velocity here? What do you have to do? Velocity is distance over time. What is the total distance? Total distance from Oldenburg to Wilhelmshaven and back 100. So total distance 50 kilometers plus 50 kilometers. What is total time? In the morning, I'm alone at the street. I can drive on average 100 kilometers per hour. This afternoon, everybody is going back 1.5 hours. Yes. So the first one would be 0.5 hours and then 1 hour. So we obtain 100 kilometer and 1.5 hours. Then overall Oldenburg, Wilhelmshaven, Oldenburg is then calculated by total distance over total time. And this is 100 over 1.5 kilometer per hour. And this is, if you calculate this, 200 over 3 kilometers. Yes, and this is then 66.6 kilometers per hour. Well, and this is, of course, not the same as the arithmetic mean of the single velocities, because this would be 100 kilometers per hour plus 50 kilometers per hour over 2 would be 75 kilometers per hour. Well, of course, this is nevertheless also an average velocity. Well, maybe it's also intuitively clear that it has to be less than 75 kilometers because the time I spent on the street with 50 kilometers per hour is much longer than the time I spent the same distance with 100 kilometers per hour. Well, and then you can generally show that if you have a task like this, then you have to use the so-called harmonic mean. And the harmonic mean is defined as the sum of 1 over xi to the power of minus 1 times 1 over n to the power of minus 1. Or let me write it in another way. Let's write this also as xi to the power of minus I. I equals 1 until n. Or this is then the same as 1 over 1 over x1 plus x2 plus 1 over xn times 1 over n to the power of minus 1. So what we see here is that all three means look like more or less the same. Here you are interchanging the plus with a multiplication sign, and you move this 1 over n, which you multiply with a bracket, just up to the power of 1 over n. And in the harmonic mean, we see that you just write on every part compared to the arithmetic mean, just a minus 1 as an exponent. Well, and then let's see if we really can calculate the average velocity via this harmonic mean. Well, x1 and x2, these are our two velocities. So what we obtain is 1 over 100 plus 1 over 50 times 1 over 2 to minus 1. So, of course, you can type this in some mathematical product and then you will get out the result. Let's see if we can do this together. What do I have to do now if I want to do it by hand? Well, if you want, since we are only still 4 guys, we can also communicate via your microphones. We want to see if this is the same as 66 point period 6. Are you able to do this? What is this? The inverse of 1 over 2 is I think class 5 in school. Overall, everything of this is class 5 in school. Or it should be. This is 2, of course. So we have 2 over 1 plus 100 plus 1 over 50. How do we go further? What do you do if you have two different denominators? We should have the same denominators. So 2 over 1 over 100 plus 2 over 100. And then we have 2 over 3 over 100. And then you have to take the inverse of 3 over 100 and you have 2 over 3 times 100. And this is surprisingly the same as this. Okay, so then we are going back to our data set and we want to calculate the harmonic mean. if we want to calculate the harmonic mean, then of course we need the inverse of every data point. 1 over data, oops, 1. And we need the sum of the inverse. That's not the sum, this one. Yeah. And what is happening here? Why do we have a 0 here? Oh, it was too small, therefore. Then we need the inverse of the sum. And we need 1 over n, the inverse, times the inverse of the sum. So we have to multiply this by 15. This would be our harmonic mean. And if I'm right, then we have also a formula in order to, oops, not this one, but the original data, of course. This is also one reason why I'm doing these calculations here live with you, that you also see if you are manipulating your data in some software package, then you always should know what you are doing. And as you have seen, I just chose here, in order to calculate the harmonic mean, the wrong data. And it is really important that you always have an idea what should come out, what is a plausible result of my manipulation of the data. And then you quite fast see when you are doing something wrong. Okay, what else should we do? So, calculate arithmetic, geometric, harmonic, mean, and the median. What is the median of the distribution? What do you have to do if you want to calculate the median of a sample? I hope you have talked about the median of a distribution in your introductory courses. And in general, you should know what a median is. The middle number, yes. So then if you interpret your definition, the middle number, how can you obtain the middle number out of these data points? What do you have to do then? Anybody else? Well, if you only know what it is, but you cannot calculate it, then you have a problem. So you would just feed in the data in SPSS or something like this and then press enter. What would you do? Well, in order to be a little bit more exact, the median is the number or the data point which divides your distribution into equally large parts when you have ordered your data points. And for this, we then need that we order these data points from the lowest. This is, I think, here 150 to the largest, and this is supposed to be by I 195. Well, of course, doing this, we can do it, of course, by hand, sorting this data, but there is also a possibility to use your program, and then you find here data, sort. Oh, I need one more, this one. Then we type in here. This one. This bracket, and starting from the lowest. Okay, and now we have it. And now we have 15. So what is then the median of this distribution? 163. Why do you say 163? You took the average of 7 and 8, but we have 15. So if we take 8, then we have the same number, 7 here and 7 here. So if we have an odd number for our data set, then you really can choose the value in the middle, because 164 here, this is the data point which divides just, we have 50% then lower and 50% higher. So this would be our median. And let's see if we are right. Median. And we take also the original data and 164. Well, And already calculating these different measures, averaging our data set, we get also already some additional information out of it. Because what we see here is that the median is lower than the arithmetic mean. And since we know this, we also already know that our distribution is not symmetric. Because if these two numbers would coincide, then we know that our distribution would be symmetric. Since the median is lower than the arithmetic mean, then we know, well, there are slightly a little bit more little people in our class. Okay, but in order to examine in a more detailed way the shape of our distribution, we go now to the measures to calculate them, and this is then MAD. This is mean average distance, the variance, standard deviation, and the coefficient of variation. Hopefully you have also already heard of all distance measures. So, mean average distance. This is with respect to the arithmetic mean now, everything of this. Every number is calculated with respect to the arithmetic mean. Then let's take a new slide. Mean average distance. This is defined as 1 over n, and then every distance from the single data point with respect to the arithmetic mean, taking the absolute value. So for this, let's move this together and we need at first the distances with respect to the arithmetic mean. So absolute distances of every single data point. And so we obtain abs is taking the absolute value of 176 minus 170, and we want to copy the formula then down for every data point, and therefore we have to fix this arithmetic mean, and this is done via setting a dollar in front of our number here. Oops, not H, D minus G. Oh. Again, why is it not G, not D? Now we have it down and summing up. And dividing by 15. This is the mean average distance. Variance is defined how? This was the average squared distance of every data point. So 1 over n sum over xi minus x bar squared. Let's do this. Squared distance, so equals again 176 minus arithmetic mean. There you can use F4 in order to get these two dollar signs and squared. Again, summing up and dividing this number by 15. So this is then the variance. Standard deviation is what? Well, standard deviation is just the root of other variance. Oops, times. So root of 1 over n times xi minus x bar squared. So we take then just root of standard deviation. And variation the variation coefficient. Have you heard about this? Well, variation coefficient, this means if you have in general large numbers, then of course you shouldn't be surprised that if you have a data set with large numbers compared to a data set with small numbers, that the standard deviation is larger of the data set with the large numbers. This should not, this could, this need not be the case, but in general, this would be the empirical result. And then this standard deviation is a measure for the fluctuation around the average in your data set. And yeah, then you want to say something like in one data set, the data is fluctuating more than in the other data set. But if the number just only depends on how large are your numbers in general, so compare maybe you are collecting price data in euros and collecting price data in cents. Then, of course, the standard deviation of your cent sample will be larger than your euro sample. And in order to get a general measure for your fluctuation, therefore, we need a measure which has no unit, and therefore we calculate the so-called variation coefficient, and this is just the standard deviation divided by the average, by the arithmetic mean. So variation coefficient is standard deviation over the arithmetic mean. Well, so in the end, we then calculate our 15.29 over our arithmetic mean. Okay, then the last part which we want to do is that we want to calculate another data set with now female students. In general, females are not are a little bit smaller than men, and therefore we want now to create a data set around 165 centimeters with a maximum deviation of 20 centimeters. And having already created a data set around 175 plus minus 25, we can just use what we have done here for our females. So then let's copy this here. Then we want only 11. And now it should fluctuate around 165 and plus minus 20 centimeters means then just reducing our 50 to 40. Copying this formula downward, we obtain a data set for the length of female students. So you see, always pressing enter means generating new data, but we want to fix it now with this data set. So let's go also there in order to format this a little bit. And now what we want to create is a contingency table where we also sort our data in some classes from 0 to 155, 155 to 170, and so on. So for this, we then also order our data. And here we have now our two ordered data sets. And we will use a new spreadsheet for this. The length of our male students and length female. In the ordered case, we have then this one here. And this one here. And so contingency table means now our data differs in two dimensions. The one dimension is of course length, and the other dimension is are we male or female. And therefore we create our contingency table, male, female, and we have our classes from 0 to 155 centimeters and then moving up to 200 with steps of 15 centimeters. And what you see here also that I took here on this side always a round bracket. And this means if you are exactly 170 centimeters, then you do not are a member anymore of this class, but of the next one. So this bracket here means including the limit of the interval. So our length classes 0 to 155, and I should also use these brackets. And then 155 to 170, 100, 70 to 185, and the last one 185 to 200. So, how many people out of our now 26 people are male and below 155 centimeters? Then we see here this is our 2 between 155 and 170. This is 1, 2, 3, 4, 5, 6. 170 until 185. This is 4. And 185. These are 3. And female, there we have 2. Then we have until 70 is 1, 2, 3, 4, 5, 6. And 170 to 185 is 3. And 0 for the largest class. So, in order to calculate now the marginal distribution of this contingency table, what do we have to do then? Therefore, we want to know how many people out of our sample are now relative to the full distribution. So our 26 people in the interval 0 to 155 centimeters. And for this, we just sum up here our columns. And then out of course, we want to know how many people out of our 26 overall people are male and female. And this means we also take just the sum here. So this is then the absolute number. And this, of course, are my overall number, 11 plus 15. And let's move this into the middle. So, these were our absolute distribution. Well, and then in order to make statements about probabilities, therefore we have to calculate the relative distribution. So what we now want to know is how many people are relatively male and in parallel lower than 155 centimeters. What is the empirical probability that I am male and smaller than 155 centimeters? What do I have then to do? So this is the relative distribution, and there the empirical one. Again, the question is now, what is the probability that I'm male and smaller than 155 centimeters? What do I have to calculate? Well, you said that you already heard about contingency tables. And of course, looking at your data set, then you should also be able to answer this question. Well, in the end, we have two guys smaller than 155 centimeters and male, and we have an overall number of 26 people. Therefore, it is 2 over 26. So this over the total number. And again, since we have to calculate every number or divide every number by 26, we again fix it by F4 and then copy this one here. And these are now our probabilities to be, for example, female and in the interval 170 to 185. These are three people, and therefore 3 over 26 is 11.54%. So this would be then not the absolute values, but the probabilities. Well, and here now the cumulated or so-called marginal probability to be male in our data set is then, of course, the total number of males divided by the overall number. So our 15 divided by 26 and this one, and here also our 4 divided by 26, and again copying this down here, formatting it in percent, and of course we can also then calculate both in order to having calculated every possible probability in order to be in the overall interval between 0 and 200 centimeters, and male or female, this is then of course 100%. And the last one is that we so-called calculate the so-called theoretical relative distribution. And what is this? With the assumption that both attributes are independent. What means independency? This hopefully you also know from your introductory course in statistics. Two events are independent, or if events are independent, then I have to multiply the probabilities. So take, for example, the famous coin experiment, flipping a coin, heads or tail, and in order to obtain a head with one throw, then you have the probability 1/2, and the probability of the two events, first throw head, second throw head, should be independent with a fair coin, and then both probabilities are 1/2, and the probability to obtain within two throws in a row 2 times head is then 1/2 times 1/2 is 1/4. And therefore, if our attributes would be independent, then we have to multiply the probability here, or let's also again write down it in percent. So the probability for some guy to have a length between 0 and 155 centimeters, not knowing if he is male or she, or if the person is male or female, is 15%, and the overall probability to be male is 57.69%. So if both attributes would be independent, then the probability to be male, or the theoretical probability to be male and to be smaller than 155 centimeters would be 15% times 57%. So 15% times 57. And this, of course, we have to do for every column. So here we calculate then 46% times 57% and so on. And for the male people, of course, 15% times 42. And these are now our empirical distribution, or theoretical distribution. Well, and now we compare our theoretical distribution these numbers with our empirical probabilities. And what we see then is, of course, that these numbers here are differing. And this means that our two attributes are not statistically independent. Let's take this here. So, comparing the empirical and theoretical probabilities, we see that they are differing, and therefore the attribute male, female, and length are not independent. So, for example, here 8.88% unequal 7.69%. Well, of course, this is not very surprisingly, since in general, as we have calculated our data, or how did we obtain our data, there we said that in general the female persons should fluctuate around a lower average than the male people, and therefore we should also expect that these two attributes depend in some way to each other. Well, but still, this is only a descriptive analysis. And then starting from this, we also can formulate then the hypothesis. Well, how statistically robust is our hypothesis that we say these two attributes depend on each other? Because of course we say we have to admit here that we haven't looked at every male and female person in our country or in the world. So maybe it could be that it is just an outcome of our specific sample which we have chosen here. And therefore, we also then have to test this hypothesis, and this I think we will then do in the end of this lecture. That we then have also a measure given an error probability of, for example, 1%, how much can we rely on the assumption that our two attributes are independent? So maybe some of you have heard of this, and this is called the so-called chi-squared test for independence. This one is Greek letter chi. Have you heard about this already? Chi-square test? No, then you will hear it here in this lecture. Okay, well, I think we end this lecture for today. Since then, we will also do the other revision about probability, and then I will also talk about in the end with you about the central limit theorem, which I have already mentioned. Okay, then let's see next week and think of the topic which you want to choose for your term paper.